This is second lecture on the longitudinal stability. In the previous lecture, we've reviewed the importance of CG location and also defined the neutral point. And in this second lecture, we will derive the neutral point equation. And we have this aircraft again, and it is during cruise condition. And now let's do some analysis on this aircraft, especially for its moment. And we are trying to write down its moment equation. First of all, okay, so we have the CG, and there is a original moment acting on the aircraft, which is M0. And let's see what happens further on this aircraft. And we know there will be a lift force from the wing body combination, and also there is a weight W, and it's acting on CG. And on the elevator, we have a lift LT. And apart from W, LWB and LT will contribute to the moment. And now we need to determine their moment arm. For LWB, and we know its distance from the leading edge is XWB, and CG is from the leading edge is X, and the moment arm for LT is small lt, okay? Instead of writing down directly XWB or X, we define a ratio. So we use HWB equals XWB divided by the mean aerodynamic chord, and then we have H equals X divided by C bar, mean aerodynamic chord. Okay, so now we can write down the moment equation about the CG. So the total moment M equals M0 plus the moment produced by the lift from the wing body is positive, and the restoring moment from the elevator LT is negative. So we have the moment equation, and sometimes we are interested in its coefficient form, and now we need to do the non-dimensionalization. So for each component on the right hand side, and since the first is M0, it's a moment, so its denominator is half rho v squared times SC bar, and LWB is force, so we divide half rho v squared times S. The same for LT, it's half rho v squared times ST, and the common denominator then is half rho v squared times S times ST times C bar. So for the pitching moment left hand side and the right hand side, we divide the same denominator, and we do some manipulation. Eventually we can rewrite the pitching moment equation as in the non-dimensional form, Cm. Okay, it looks more concise than the dimensional form. And for the moment, we use moment coefficient. For force, we use lift coefficient. So we have CLWB and CLT. That's the lift coefficient for wing body and the lift coefficient for elevator. And that's for this slide. So I'm copying the non-dimensional form of the pitching moment equation in here. And now let's focus on the last term in the right hand side. In the bracket, we have ST divided by S times LT divided by C bar. And as usual, we can define this as the tail volume coefficient and replace it by VT bar. Okay, so, and now let's analyze the CLT, the lift coefficient at elevator tail. Okay, and the CLT can be written down as three parts. First is AT times alpha plus eta t minus epsilon. And the second part is A2 times eta. And the third part is A3 times beta eta. And we may get confused by a lot of symbols or notations, and then we can do a bit analysis through this plot. And this plot is from the textbook Flight Dynamics Principles. Okay, and so we have the wing at the beginning, and the angle of attack is alpha. And we have the tail plane at the behind the wing. So the tail plane is also comprised by three parts: the main tail plane, elevator, and the trim tab. Okay, so we first go to the first part in the right hand side. Alpha t, at is the lift coefficient slope for the tail plane, and times the angle of attack, then alpha plus eta t minus epsilon. So alpha is the angle of attack of the wing, and eta t is the setting angle of the tail plane, and epsilon is the downwash angle. So we've seen the downwash angle before and analyzed through a similar plot. So these three components, alpha plus eta t minus epsilon, is the effective angle of attack for at the tail plane. So, and the second part is A2 times eta t. A2 is a constant related with elevator angle eta, and that's the contribution from the elevator angle to the lift coefficient. And the last is the trim tab angle times A3. Beta eta is the trim tab angle. So that will also, you deflect the trim tab, and that will contribute to the lift coefficient. So you see the CLT is actually contributed by three components: the tail plane, actual tail plane, main tail plane, elevator, and the trim tab. Okay, so we just plug in CLT, and then we can have this non-dimensional pitching moment equation. Okay, so let's see. In the trimmed flight, the total pitching moment is 0, equals 0. So the left-hand side becomes 0, and then we can rewrite this pitching moment coefficient equation becomes 0. So let's continue work from this non-dimensional pitching moment equation. And the target now is, since we are interested in the elevator deflection, and we want to put the elevator angle explicit. So we take Vt bar times A2 times eta trim, and we add the subsequent trim, because now we are starting the trimmed condition. And then this eta trim becomes explicit on the left hand side, and the right hand side is combined by the other terms. So we, on both sides, we divide Vt bar times A2. So now eta trim is really explicit. Okay, and now what we are changing is replace CL wing body as A times alpha. A is wing body lift curve slope, alpha is angle of attack, and we have this. Okay, so one more step. So we are working on the last term in the bracket on the right hand side. So we can replace A minus epsilon by A1 minus partial epsilon partial alpha. So that's downwash angle change rate with respect to the angle of attack change. So we have eta trim. And you may wonder why we want to make eta trim explicit. And this is because eta, the elevator deflection angle, is related directly with the restoring moment, elevator moment, mt. And before, we have this plot on the right hand side. We've seen that. And this plot helps us to derive or determine the neutral point, right? And since mt, if we do any flight test, mt is not measurable, but we can measure the elevator trim angle. So we can get the determine through flight tests by measuring eta angle, and then we can get the neutral point of the aircraft. So that's why eta trim is so important. So it's related. The answer is it's related with the restoring moment mt. Okay. The task now is to derive the neutral point equation, and it will be derived on the stick fix condition. What does stick fix mean? And stick fix means pilot won't control the stick. There will be no movement of the stick, so there will be no elevator movement. And in a box, we have this pitching moment equation, and we've derived this earlier. And now let's walk further from here. And first of all, if we do the difference, partial CM, partial CL, so essentially, which means we do difference of CL, and then we get this expression. And now we are focusing on the last term of on the right hand side, the third term. Okay. First of all, alpha t is the tail plane angle of attack. It equals alpha minus epsilon. Alpha is the angle of attack of the wing body or wing, and my epsilon is a downwash angle. So downwash essentially reduce effective angle of attack for the tail plane, and we've discussed this earlier. Okay, so we are focusing on the last term. We can take it out and rewrite. So we are replacing alpha t by alpha minus epsilon, and we just take alpha out of that small bracket, and then we have alpha times 1 minus partial epsilon partial alpha. And because we know partial alpha partial CL, that's for the wing body or wing, it equals 1 over A. That's a lift curve slope. And we can eliminate the difference, partial difference now. So it equals AT divided by A times 1 minus partial epsilon partial alpha times the tail volume coefficient. So this is what we have on the right hand side, the last term. And if we plug it into the original equation, the second equation from the top, and it can be written like this way. And because we know Cm, that the pitching moment inherited or original pitching moment is a constant, so partial Cm 0, partial CL is 0. And so this equation can be simplified, especially on the right hand side. At the neutral point, also we know the total moment is 0. And then the partial CM partial CL is also 0. Okay, and then we have the right hand side being 0. Okay, so it's much simplified from the original equation. And if we take the rest of the terms to the right hand side, then Hn is a neutral point location. It equals HWB, the aerodynamic center of the wing body combination plus that part. So this is what we want, the neutral point equation. And you can see it's related with the aerodynamic center of the wing body, and also related with the especially the downwash angle change with respect to the angle of attack change. Okay, this is a neutral point equation we've derived. Now let's do a bit more discussion, and especially for the definition of each quantity. And I'm not reading all the notations, but I want to highlight partial epsilon partial alpha, and it is the rate of change of downwash angle with respect to angle of attack. And for this quantity, this ratio is about 0.3 to 0.4 for regular aircraft or passenger aircraft. And you can see it's not really small, it's kind of significant for the neutral point. And the Hn, since you can see it's a combination of the aerodynamic center of the wing body plus some correction factors, especially determined by the downwash effect. And in practice, we can take Hn, the neutral point, as the aerodynamic center of the whole aircraft by taking taking the tail portion into account. So that's the important part for the neutral point equation. Now we can close the derivation of the neutral point equation, and so far we should understand why the CG is important, CG location is important, and the neutral point equation, how it is derived.